with 25A, we send 1,000, well, really over 1,000 milliliters of blood through the glomeruli every minute. That's amazing. And from that, we filter 120 up to 125-ish milliliters. We're going to remove about 10% of that fluid. Excuse me. And I'll come back to that momentarily elsewhere on the slide. Every day, the renal tubules will process 180 liters of fluid. That doesn't mean that we eliminate 180 liters of fluid as urine, because the job of the renal tubules is to make adjustments, right? Including adjustments in water content so that we're not losing all of that water. And somehow, out of that 180 liters, we only eliminate about 1.5 liters as urine every day. That's, wow. Wow. What a huge impact the tubules make. The kidneys are big spenders, which I think maybe you already knew from 241, that they are very metabolically active. They spend a lot of oxygen or demand a lot of oxygen. Urine formation is the end result of what nephrons do. Initially, they make filtrate. We already know, right, that filtration is occurring in the renal corpuscle, okay? And filtrate is everything but cells, proteins, protein-bound substances. They might be small, but if they're sort of attached to larger proteins, then we have a hard time drawing them into the filtrate, okay? And then also the fluid that these solutes, right, sort of pull on or keep behind due to osmotic pressure. We already know that renal tubules perform reabsorption and secretion. Okay. Reabsorption you might think of it as reclaiming or reclamation. Or you might think of it as keeping. This is the stuff we're going to keep, okay? Whereas if tubule cells secrete, then we're sending things into filtrate rather than out of filtrate, all right? Gosh, I'm kind of croaky today. On slide 37 is a really, really, really oversimplified model of the blood flow and configuration of at least the proximal nephron, where we can see that capsule, that Bowman's capsule. The illustrators so simplified this that we really can't even see the layers of the capsule. We can see some loops making up a glomerulus, right? And we already know that what happens here is filtration. Whereas what happens here is both absorption and secretion, okay? Next slide. Glomerular filtration doesn't require any ATP. It's passive, okay? Which might surprise you because I just mentioned that nephrons are big spenders. They require a lot of oxygen. Well, if filtration is passive, if it doesn't require ATP, if it doesn't require a final electron acceptor, then how do kidneys spend? What are they spending on if they're not spending on filtration? It's probably pretty obvious they're spending on reabsorption and especially secretion, because, secretion is really forcibly placing things that we want to eliminate into the filtrate. We'll come back to both reabsorption and secretion later in this chapter, and for many slides to come, we'll just focus on filtration. We've met so many membranes this quarter. For instance, the respiratory membrane. Well, sure enough, there's a filtration membrane. And the filtration membrane has 3 layers, just as the respiratory membrane did. The epithelial cells of those glomerular capillaries, epithelial cells of the glomerulus, okay? Our podocyte foot processes, aka the visceral layer of the Bowman's capsule, okay? And the scant basement membrane, or really basement membranes, that are fused together. So very, very similar to what we saw in, for instance, the lungs, okay? Recall that in between adjacent podocyte foot processes are filtration slits, and stretched across those are super thin, essentially plasma membrane. Slit diaphragms. And I think, in the next slide, we're just revisiting that image that we saw earlier so that we can see, this image that we already studied, it actually reiterates for us who the components of the filtration membrane are, okay? So just kind of putting it together. On their way through the filtration membrane, macromolecules they're large, and if they attempt to sort of follow the fluid, they will get engulfed and phagocytosed, actually that's redundant, engulfed and broken down by glomerular mesangial cells. The packing peanuts that are actually in the renal corpuscle, whereas extraglomerular mesangial cells are outside the renal corpuscle. The filtration membrane will allow molecules that are smaller than 3 nanometers to pass without getting sort of hung up, okay? That means water can pass, glucose molecules can pass, amino acids can pass, nitrogenous waste, urea, can obviously pass, okay? No problem, they're small enough. Plasma proteins, however, are too large, and they stay behind. They also keep behind with them anything that's bound to them, okay? Certain drugs, for instance, will bind to proteins, okay? And those will not get stripped via filtration from the blood, okay? Therefore, the cells, the plasma proteins, the protein-bound substances in the blood, they maintain that osmotic pressure that keeps enough fluid in our circulatory system to continue to call it fluid. I don't want my blood to turn into crystals. No, thank you. Next slide. So when we were studying respiratory system, and gosh, I don't remember what chapter this was. I think it was the vessels chapter. We were studying also the forces that pull and push fluid in and out of capillaries. So we've actually played this sort of arrow game before, and so that you don't have to wait. Even though I want to talk about 41, if you quickly glance at 42, you'll see what I mean by the arrows game. Then you're all rolling your eyes now. Let's go back to 41. Okay, the chief forces that are at play here that decide whether fluid enters the capsular space or stays within the lumen of the glomerulus are the hydrostatic pressure in the glomerulus, in those glomerular capillaries. Okay. The osmotic pressure in filtrate, aka in the capsular space. Okay. The hydrostatic pressure in the capsular space. Okay. And the osmotic pressure in glomerular capillary. Okay, so why are these listed this way? Why in this order? Because if we were thinking about arrows, okay, the hydrostatic pressure in glomerular capillaries is pushing fluid out of the capillaries. The osmotic pressure in capsular space would be pulling, drawing fluid out. In other words, these are the outward forces, okay? And this chunk down here, these are the inward forces. Hydrostatic pressure within capsular space would be pushing inward into the glomerular capillaries. If it won the tug of war, the solutes in the glomerular capillaries are pulling on fluid, pulling back in, okay? So what we want to pay attention to is which arrows are sort of winning this tug of war, okay? Well, in the glomerulus, blood pressure is actually remarkably high. In most capillary beds in the body, blood pressure is about 26, as you may remember, millimeters of mercury, okay? But in the glomerulus, dang! Blood pressure is about 55 millimeters of mercury. That's very high. Why? Why is it so high? Because the efferent arteriole that drains the glomerulus, it's actually under really, really high, or not, I shouldn't say that. It offers high resistance, in part because it's got a narrow diameter, okay? And offering high resistance means that the blood flowing through the glomerulus is not only under high pressure, but it's also forced to slow down, giving the nephron enough time to filter maximally, okay? So this arrow represents an outward arrow or outward force of about 55 millimeters of mercury, okay? This arrow it's actually treated as 0. Okay? Why? There's always a drain open in this bathtub. The capsular space is always being drained into, or the fluid inside that capsular space is always being drained into the renal tubule. Right? It's not like there's a door or a valve or anything that the filtrate needs to go through in order to enter the renal tubule. So kind of the same principle as the lymphatic system keeping hydrostatic pressure of interstitial fluid low. Kind of the same idea, okay? This arrow here (15 millimeters of mercury). Why so low? Same reason. That capsular space is always being drained, okay? And this arrow here representing the solutes that are too large or too bound to escape the blood, at least in the renal corpuscle. It's about 30 millimeters of mercury, okay? And hopefully it's old news or very intuitive for you that you need to add together your outward arrows, add together your inward arrows, and whatever number is higher wins, okay? Well, that winner is, or that difference, or what I should really say, is net filtration pressure, okay? And it's probably pretty obvious, right? 55 total versus 45 total, that outward forces win by about 10 millimeters of mercury, okay? Net filtration pressure is the main determinant of what's called glomerular filtration rate. We'll come back to that very soon. Okay, we are looking at 42, which really just reiterates what we just did in a very visual way. We were also visual, but this is maybe a little more clear for you, okay? What's not shown? Yeah, there's an outward arrow that's not shown. It's confusing for me to draw it here, though. In fact, I'm not going to do that. You're never going to see what I just did. There's an arrow, right, that's missing. Why is it missing? Because it's 0 anyway. It's 0 anyway. The osmotic pressure applied by solutes in the capsular space, it's negligible. We treat it as 0 anyway. So that's kind of nice to just sort of not worry about it. Okay, next slide is... Gosh, I'm trying to remember whether I covered this in another lecture. Just a second. Nah, we're all good. Glomerular filtration rate is the amount of filtrate that the kidneys form together, okay, per minute. And it's normally 120 to 125 milliliters of or per minute. And we actually already established that in, gosh, a really recent slide 36. So we just didn't call it anything, and now we're calling it glomerular filtration rate, okay? And the main influences on glomerular filtration rate include net filtration pressure, okay? The total surface area that glomerular capillaries offer, okay? And the permeability of the filtration membrane. Well, how much can we adjust the permeability of the filtration membrane in a healthy body? Not much, okay? Can we adjust the total surface area that's available for filtration? A little bit. Surprisingly, or it may surprise you to find out that glomerular mesangial cells can actually contract around the, or because they're surrounding, right, the glomerular capillaries, and therefore, or thereby, adjust the surface area that's actually available for filtration. So a little bit of alteration there, but the main factor that can be used to regulate GFR, glomerular filtration rate, is that pressure, because we can, not surprisingly, change the diameter of the arterioles that both feed and drain the glomerulus, and therefore affect the blood pressure really within the glomerulus. And that blood pressure was that 55 millimeters of mercury that we just talked about, that winner of the tug of war, okay? That's what we can make adjustments to. That's pretty important.
Bear with me while I switch files here.
Left off. We had just, yes, sweetheart.
Hold on.
Okay. Yes. That's fine.
Sorry, guys.
Anyway, we had just established that glomerular filtration rate is the amount of urine that the kidneys filter, or not urine, the amount of filtrate that the kidneys produce, right, over or per unit time, all right? And next, what we want to talk about is the regulation of glomerular filtration. And we already know, I mean, we started this in chapter 16, right, that there's a relationship between urine output and blood volume, and we already know that blood volume and blood pressure are coupled, right? Whatever blood volume is doing, blood pressure is doing, and vice versa, okay? Well, if GFR is relatively high, then the nephrons are actually going to end up producing more urine. If urine volume is high, then what happens to blood volume? It decreases, right? And vice versa. If GFR is relatively low, then the kidneys are making less urine. What happens to blood volume? It increases. And this is a horse that we killed and buried really at the beginning of the course. So that hopefully feels fine. Why is it important to minimize how much glomerular filtration rate is allowed to change? Why is it so important to keep those changes to a minimum? Well, one way to think of that is, suppose we increased mean arterial pressure from 100 millimeters of mercury to 125 millimeters of mercury, all right? And we didn't have any regulatory mechanisms in place. We didn't make adjustments to reflect that, okay? We didn't make adjustments in glomerular filtration rate. What would happen? Well, we would end up with a urine output close to 45 liters per day. Can we afford to urinate out 45 liters per day? No way, right? If the filtration rate is too high, then we're at risk, at very least, of dehydration. We're at risk of losing important solutes, not to mention ions, right? Slow down, you move too fast, you gotta make filtration last. Whereas if glomerular filtration rate is too low, then the issue is that those metabolic toxins, many of which are acidic, right? They end up lingering. We end up keeping them rather than eliminating them. So dangerous either way, and that's why we want to keep that window in a sort of safe range, if you will. And we have 4 major regulatory mechanisms in place. 2 of these are intrinsic, and 2 of these are extrinsic. The intrinsic controls hopefully will make sense for you, because we've been using the term intrinsic all quarter long. Intrinsic, most of you have learned to think of as from within. I can take care of this myself, thank you. I don't need to recruit help, right? Whereas extrinsic, which we've also been using all quarter long, you might think of as from without, or, you know, that I like to use recruitment. Let's recruit help. Recruit the help of adjacent tissues, or recruit the help of other organs, or recruit the help of other organ systems, which is the case in this particular context, okay? When blood pressure changes are extreme, like dangerously extreme, it's the extrinsic controls that will step in and take over. And we'll come back to that. All of these regulatory mechanisms are going to alter glomerular hydrostatic pressure. And just recently, a couple of slides ago, we talked about how important the hydrostatic pressure, or the push, if you will, of fluid outward within the glomerular capillaries is to ensuring fluid moves out of those capillaries and into the capsular space. If we make adjustments to that hydrostatic pressure, then we may be favoring or inhibiting filtration. Let's move to the next slide. Just an overview of the intrinsic controls, which are often, in this context, also referred to as renal autoregulation, which is nice because the root auto means self. Thanks, I'll do this by myself. All right. There are 2 major mechanisms, the myogenic mechanism and the tubuloglomerular feedback mechanism. And these guys are going to make adjustments to GFR as long as our mean arterial pressure is somewhere in the range between about 90 millimeters of mercury and 180 millimeters of mercury. If our blood pressure is higher than that, then other controls will step in. If our blood pressure is lower than that, then other controls will step in. Let's look at the myogenic mechanism, which is something that actually is relevant for the whole body. It's not a kidney-only thing. And it's the trend, the tendency, if you will, of muscle cells to contract in response to stretch. It isn't quite a reflex, or at least we don't typically apply that word reflex in this case, even though it is an automated response, because we don't require the nervous system to elicit a motor plan in order to elicit that stretch, or not stretch, but contraction response, okay? Well, smooth muscle is no exception. Smooth muscle also will contract when it's stretched. And since we so often see smooth muscle in the walls of hollow organs, including tubes, including teeny tiny tubes, that means that whenever those hollow organs are very full, they're distended, they're going to stretch that wall and therefore stretch those smooth muscle cells, okay? Recall from recent lecture that the glomerular capillaries are fed by an afferent arterial and drained by an efferent arterial. All right. Well, when we have high blood pressure, the smooth muscle cells in the wall of the afferent arterial will become stretched and in response will contract. And that contraction or constriction lowers hydrostatic pressure within the glomerular capillaries and therefore also lowers or decreases glomerular filtration rate. Okay, same principle if we have relatively low pressure or even homeostatic norm pressure, then that afferent arterial is allowed to relax. Those smooth muscle cells are allowed to relax and the lumen is dilated, and therefore we keep that hydrostatic pressure nice and high. We keep that glomerular filtration rate nice and high. Let's talk about the glomerular feedback mechanism, which really revolves around the juxtaglomerular complex. I know everyone's groaning, but one nice thing is, yeah, this is a mouthful. I know. But look, so is this, right? And they both have glomerular in their terms. So hopefully built-in mnemonic there. Let's review really quickly who the components of the juxtaglomerular complex are. Remember, in the ascending limb of the nephron loop, we have specialized cells called macula densa cells, and primarily in the afferent arterial, we have specialized cells called granular cells. All right, and then all of these kind of lavender, not literally lavender, just color-coded cells are mesangial cells. Those that are in the renal corpuscle are often called glomerular mesangial cells, whereas those here in this sort of wedge or triangle between macula densa cells and our two arterioles, these are often called extra, as an outside, extra glomerular mesangial cells. Just a bit of review, all right? Well, when our GFR is very high, then I get to sing my song again. Slow down, you move too fast. The nephron doesn't have enough time to reabsorb maximally, to reabsorb efficiently. And therefore, sodium, potassium, and chloride ions remain high in the filtrate, even in the distal tubule, okay? Well, macula densa cells are positioned in the distal tubule, and they act as sensory receptors. What are they sensitive to? Those high ion concentrations. And what happens is that they actually absorb excess ions and in response secrete ATP. And ATP, you may already know, is yet another powerful vasoconstrictor. What happens is those mesangial cells, those sort of packing peanuts that we saw, they will metabolize that ATP that the macula densa cells secreted into adenosine. And then adenosine in turn acts as a cellular signal to trigger granular cells to contract. Well, where are granular cells? The afferent arterial primarily, okay? And therefore, once again, we're going to lower that hydrostatic pressure within glomerular capillaries. We're going to lower our GFR. And notice that at the bottom of the slide, I gave you a couple of thinking questions. And if we have time today, we'll come back to those. Let's look at our extrinsic controls. The extrinsic controls, again, they're going to compensate for dangerously extreme changes in blood pressure, okay? And their goal is really to change blood pressure, but because glomerular filtration rate is a function of blood pressure, it also gets changed, okay? Now, it's especially important that we think about the consequence of blood pressure being very, as in dangerously, extremely low, because if blood pressure falls to, say, about 70 millimeters of mercury, filtration stops, urine production stops, and that's not an option. There are two extrinsic controls, at least major extrinsic controls, and the good news is that they're going to look very familiar. We talked about both of these already this quarter, so just mostly review, which is nice. Let's move on and look at the neural mechanism, or the sympathetic mechanism. Hopefully this image looks very familiar and old. We saw this in the lecture called 242 Survival Kit. We saw this again and again and again in the heart lecture. It's a tesserized figure, so only you, my students, have seen it. And recall that we played with stimuli like high CO2, low CO2, high blood pressure, low blood pressure, right? Well, let's suppose this time around, low blood pressure. Let's also write legibly. It's a new idea. All right, there we go. Low blood pressure will stimulate infrequent action potentials along our sensory routes. The medulla will respond in turn by sending relatively infrequent action potentials out along our parasympathetic route and relatively frequent action potentials out along our sympathetic route. And hopefully recall that when sympathetic fibers are carrying frequent action potentials, we're going to see an increase in heart rate, cardiac output, and that's right, blood pressure. Another result is vasoconstriction, okay? And that vasoconstriction isn't limited. It includes afferent arterioles, all right? Therefore, our glomerular filtration rate decreases. Now, you might be thinking, wait, if blood pressure is low, shouldn't we increase glomerular filtration rate? I agree. I have that same question. Let's think about it. Why would the sympathetic nervous system be triggered or launched? Why? What could be going on, right? So, my favorite example is a zombie apocalypse or being chased by a bear, right? Where do I want blood to go? I want to shunt that blood. So that thinking question, you're spoiled. I just answered it for you. Let's move on to the hormonal mechanism, which is really renin-angiotensin-aldosterone. That mechanism that your instructor will not shut up about. We beat this horse in chapter 16. We came back to this horse in chapter 19, right? And I warned you at the very beginning of the quarter, hey, this thing is tough and this thing is not going to go away. So here we are again. And in fact, here's that column that we originally saw in chapter 16, just in case you're a visual learner, that might ring some visual bells, all right? When blood pressure is low, the baroreceptor reflex, which we just saw in the previous slide, remember we have baroreceptors in the aortic sinus and in the two carotid sinuses, okay? Those baroreceptors will also stimulate granular cells to release renin, okay? And we know that when renin enters the bloodstream, it encounters the plasma proteins called angiotensinogen. Whoops. Oh no, I think I'm good. That's good. All right. And cleaves angiotensinogen to yield angiotensin 1. Angiotensin 1 is then acted upon by ACE molecules that are made in the kidneys and lungs. and converted. Oh, I just misspelled angiotensin, didn't I? That's okay. There we go. Angiotensin 2. All right? And we know angiotensin 2 has many roles to play, many functions to offer. All right? Angiotensin 2 we know is a vasoconstrictor. So we're expecting an increase in mean arterial pressure. However, we probably didn't know that angiotensin 2 triggers constriction, be careful, in efferent arterioles. Efferent arterioles. Well, if we're constricting the post glomerular flow, then we're actually eliciting an increase in hydrostatic pressure within the glomerular capillaries, and therefore an increase in glomerular filtration rate. Also recall that efferent arterioles feed peritubular capillaries, feed the vasorecta capillaries, and therefore blood pressure is decreased in those capillaries due to that constriction, okay? And that actually facilitates better reabsorption, okay? We also know that angiotensin 2 stimulates the thirst center of the hypothalamus, stimulates the posterior lobe of the pituitary gland to secrete, that's right, ADH, and stimulates the zona glomerulosa in the adrenal cortex to release, that's right, aldosterone. Aldosterone, recall, targets the kidneys. The kidneys, in turn, will keep, reclaim, reabsorb more sodium. Wherever sodium goes, who follows? Water. So we end up keeping more sodium, more water, and in exchange, we eliminate more potassium. What happens to blood pressure? It increases. What happens to blood volume? It increases. What happens to urine volume? It decreases. Okay? So all of these roles that angiotensin 2 plays help to collectively influence blood pressure, hydrostatic pressure within the glomerular capillaries, and glomerular filtration rate. What is that collective impact? To increase or to decrease? To increase. So there's another thinking question that I answered for you. This next slide is just a nice flow chart that lays everything out for you. If you're a visual learner, the colors sometimes help. Sometimes when you're taking an exam, you can remember there were 4 colors, right? The only issue I have with this, or I guess the chief issue that I have with this image, is that I actually feel that this could be more informative. So this particular column, I would maybe add a brain in there just to remind yourself about the role that the hypothalamus and posterior pituitary play. Let's move on to our next slide. Our next slide is just sort of a wrap-up to help us think critically about glomerular filtration rate and regulation of that rate. So what I want you to do is I want you to think about what the impact of moderately high blood pressure will be on glomerular filtration rate and hydrostatic pressure within the glomerular capillaries. I want you to think about what the impact on reabsorption would be, what the impact on urine output would be. I want you to think about which regulatory mechanism or mechanisms will therefore elicit a response and what that response is. All right? And then another thinking question, I want you to, in your discussion groups, address diabetes mellitus. That's right, we're coming all the way back to diabetes mellitus. What does diabetes mellitus have to do with glomerular filtration rate? Why is diabetes the main cause of kidney disease? Really, the answer to both those questions is the same. those two questions to elicit the same answer. And I've given you a hint in the corner of the slide. Really think about those tug-of-war pressures or forces, right, that are determining the bulk movement of fluid. So go back to that slide. I think that will help a lot.